Now we can start presenting, okay? Okay, so yesterday we introduced structural operational semantics as a way to define the behavior of programs. We defined the syntax of IMP and the semantics of IMP. And we said that after defining syntax and semantics, we can start discussing about security properties of programs. And this is exactly what we will do in this lecture, which is more related to security than the previous lecture, which was more foundational for this one. And in particular, today we start discussing about information flow control. Information flow control is a very large research area. And the key idea of information flow control is studying how we protect secrets in applications. This does not sound exciting, because when we think about protecting secrets in computer science, we think about specific mechanisms. But now we will see that it is actually quite interesting, because it's something we don't actually think much about. Normally, when we want to protect secrets in computer science, we think about, for instance, access control. So we can protect secret data by putting that data inside a private area, which is protected using a password. Or we can use encryption, so that the data is transformed in a way that only if you have a shared key, you're actually able to see the plain text. And in the context of, for instance, web security, we discussed essentially sandboxing, which is something we studied in the context of frames, but even the SOP is a form of sandboxing, where the key idea is that you protect secret data by isolating processes. These kind of mechanisms are certainly useful, but were somewhat also born in the 70s, I would say. And nowadays, this kind of protection mechanism is too coarse-grained, because the key problem with all these methods to protect secrecy is that once the secret data is revealed, we don't have any way to guarantee that the secret data is not further shared with other people. If I can access the secret data using a password, I can read the data and send the data to some other party. And similarly, if I have a shared key, I can decrypt the data and then share the plain text with other parties. So the problem is that once a secret is accessible, we cannot limit its use. But if you think carefully, when we work with real-world software, that software typically has access to confidential data. For instance, think about all the applications you run in your mobile phone. This kind of application typically have access to a bunch of sensitive information. For instance, the GPS, so your position, the IMEI, which is a unique identifier of your phone, and a bunch of other things. And of course, we control what the application can access by using permissions, right? But once we grant a permission, we don't know what the application is doing with the data. If we grant permission, for instance, to use the GPS, and we grant this permission to some application which is not related to positioning, we are suspicious. But if I grant the GPS position to some application, for instance, which is designed to show me restaurants, this is not suspicious anymore. On the other hand, we don't have any proof that this application is not only showing the restaurants on the map, but is also sharing my position with some advertisement provider. So in general, once we grant access to confidential data, we cannot control how the data is used. And this leads to complicated cases, like the case of malware, which is something which I just mentioned, which is trying to disguise as a benign software, but it's actually exfiltrating sensitive information for malicious use. On the other side of the spectrum, we might have programs which are benign, so they're developed by benign developers, but since they contain bugs, like basically any program, they can leak personal data. So in general, we want to have a way to reason about the security of software which operates over confidential data as part of its intended functionality. And this is the area which is studied by information flow To to set up terminology and to have some common ground for reasoning, we make this assumption. So we assume that we work with imperative programs. We introduced imp yesterday exactly for this purpose. And since imperative programs operate on variables by reading and writing over them, we assume that variables are partitioned in two parts. And this is done by an assignment gamma, which given a variable gives me the security level of the variable. And for simplicity, we just assume for now that we have two security levels. We have low and we have high. So we discriminate essentially between variables which contain public data and variables which instead contain private data. So low confidentiality and high confidentiality variables respectively. What is the goal of the attacker? So we assume that the attacker has essentially access to the public variable, so the attacker can inspect the content of the public variable, and the goal of the attacker is to infer something about the content of the private variable just by inspecting the public variables alone. And we also make the assumption that the attacker is not only able to observe the memory, but it's also able to observe the source code of the program which is executed. What we will do now is trying to convince you that defining secrecy is no joke. So once we want to reason about the security of programs which manipulate secret data, we have to come up with a good formal definition. Otherwise, we don't have any common ground for reasoning and enforcing good behavior of programs. As a warm-up, let's start by considering following program. So we use this convention that I use H to denote variables which have high confidentiality and L to denote variables which instead have low confidentiality, so they're public. Let's consider the following program. In this first program, what we do is we read the PIN. For instance, we are modeling a bancomat, so we read the PIN. What we do is we pick the PIN that we just read, and we store the content of the PIN inside a public variable. No discussion here, right? This is totally clear that this is a security violation because I'm picking some secret data and I'm storing that secret data inside a public variable. However, we might consider also variants of this program. So what about the second program which I wrote in this slide? Is it a secure program or is it not secure? Any volunteer? Can anyone try, please? You can just unmute the microphone and speak. It's easier for me. It's
not secure.
Okay, so we got two answers. One answer is not secure. The other one, which I got in the chat, please don't use the chat, but just unmute the microphone and speak, is that this program is a little bit more secure than the other program because the attacker must know that the secret is multiplied by 2. But we said in our attacker model that we assume that the attacker has access to the source code of the program. So if the attacker has access to the source code of this program is clearly insecure. This is insecure just as the first program, because once we run this program, the attacker can leak the value of the PIN just by halving the value of the public variable L, okay? This kind of violation is typically called an explicit flow, because we have some private data which is put inside a public variable, and the content of a public variable is something like a clearly easily invertible function of the value of the confidential data. Okay, so both these programs intuitively are insecure. In particular, the second one is, the first is clearly insecure, the second one is insecure under the assumption we make that the attacker is aware of the source code of the program. Let's consider now another case. Again, I want to volunteer. So let's consider this program. In this program, I read a pin, and then if the pin is greater than 5K, I set the low variable L to 0, otherwise I set that variable to 1. Is this program secure or not?
It is limited secure, because it gives information about high-level variable
Okay,
to
so
low-level variable.
So your colleague is raising a legitimate point. In particular, there is a rich area which is called quantitative information flow, which tries to quantify the amount of information which is leaked by a program. Quantitative information flow is quite complicated in general, so we will not study quantitative information flow control in this course. So let's assume we are not reasoning about quantitative information, we're reasoning about qualitative, in a sense, information flow. And so my question is binary, is this program can be either secure or not secure. If you had to choose, would you consider this program secure or not?
Not for me.
Okay, does anyone think that the program should instead be secure? Okay, this program is not secure. In particular, technically speaking, we say that this program suffers from an implicit flow. In particular, part of the confidential information, which is the content of the private variable h, is leaked not directly by assigning this confidential data inside a public variable, but it is leaked through the control flow of our program. You might say that in this case, the loss of information is very, very low, so we don't care specifically too much about this information leakage. But if you think carefully, it's very easy to downgrade the security of the pin by using this kind of checks. Because if, in this case, I'm essentially discriminating whether the pin, if we assume we have 4 digits, is sitting on the first half of the search space of the pin or in the second half of the search space of the pin. If I apply the same reasoning by nesting multiple conditionals, I can essentially implement a form of a binary search which will eventually leak the entire pin. So if inside the then branch, I further branch over h and I check that this is greater than 7,500, I might reveal one more bit of information. And similarly for the else branch, where I can check that this is actually below 2,500. So by encoding the program in a way, in a malicious way, I might be able to actually exfiltrate the full value of the pin. And indeed, the attacker will try his best to confuse our program and to give a false feeling that there is no information leak, but actually there might be an information leak. So this program is insecure. Let's consider now this other program. Have a look and tell me whether this program is secure or not, according to your intuition.
This is insecure.
Why?
Because at the end of the while, hell will have the same value of each at starting point, the pin.
Exactly. So in this program, again, this program is insecure. Again, there is no explicit flow because I'm never taking the value of h and storing that value inside a public variable. But again, I'm building on top of the control flow of my program to eventually exfiltrate the secret. So if I just check these two instructions in isolation, these two instructions look fine because I'm putting some confidential information inside a confidential variable and some public information inside a public variable. On the other hand, the fact that this assignment is put inside a while loop, this eventually leads to a loss of confidential information. So through the control flow of this program, I might actually be able to reveal a secret. Last example. Premise, this example does not contain any typo, so this is the correct program. What do you think about this program? Is it secure or not?
Secure.
Why secure?
There is no interaction between H and hell.
I will be more careful here, because let's assume I write down my pin, and my pin is 1000. What happens in the end? In the end, it happens that the variable L is set to 1.
Oh, there is an infinite loop. Okay.
If instead I put my pin and my pin is 9000, what happens is that this program will loop forever, and the variable L will be stuck to 0. So I am actually able to tell some information about the pin. In particular, I might understand whether the pin is in the second half of the search space, if I want to brute force the pin, or in the first half of the search space. However, this is a bit of a tricky program, because the good question is whether the attacker should be able to observe termination or not. The possibility to observe termination is indeed something which is not obvious, because once I see a program running, how can I tell whether the program is terminating or not? The program might just be taking a lot of time to converge to some result. Okay, so in general, it might make sense that the attacker is not actually able to observe termination. So for an attacker who is able to observe termination, this program is clearly insecure. But for an attacker who is not able to observe termination, this program might be considered secure. Okay, so information leakage, which are enabled by the termination of the program, might be part of our threat model or not. What we do now, for simplicity, and also because a rich part of the literature on information flow control makes this assumption, is that we assume that the attacker is not able to observe termination. So this program is intuitively secure to ourselves, because if the program is looping, the attacker is not able to understand that this program is indeed looping. Okay. We discussed several ideas, and these ideas were applied in a context where variables are essentially categorized as private or public. Of course, this is a very coarse-grained view, because in real-world application, we don't reason about public data and confidential data most of the time, but we might have structured information flows. In particular, if you think about a university, you might think that the rector is allowed essentially to access any confidential file. The guest of the university can only access public files, so has no access to confidential information. But then the professors, the staff, and all the students also have access to some confidential information. And a professor intuitively should not be able to read the confidential information which belongs to the student and vice versa. Okay, so you can think that our idea of structuring information between private and confidential can be actually generalized to arbitrary security lattices. So what is a lattice, technically speaking, is a partially ordered set where we have a unique least upper bound and greatest lower bound operation. What do I mean by least upper bound and greatest lower bound? It means that for any pair of points I pick in the lattice, I'm able to find essentially one point which is on top of that and one point which is below that. And this is respectively the least one or the greatest one. For instance, if I pick professor and staff, the so-called join, so the least upper bound is rector, is the least point in the lattice which is greater than both professor and staff. If instead I pick again, let's say staff and student, the greatest lower bound, also called the meet, is guest, because it is the highest point in the lattice which is below both staff and student. This is exactly the feature of a lattice. For any pair of points you pick, you can find a join and a meet. So in general, we can extend our theory so that we don't think about private versus public, but we think about structured information flow over a security lattice. And the only difference we will make from our original definition is that rather than thinking that each variable is given high or low type, we can assign to each variable a point which we pick from the security lattice. And the key idea is that the attacker is essentially a guy who is sitting on some point of the lattice. Once we fix a point in the lattice, we essentially get a projection of the lattice, which is the public part of the information, and another part, which is the high part, which contains confidential information. For instance, if you think that the attacker is a professor, the professor might be able to read data which is labeled as professor or guest, but the professor must not be able to analyze data which is owned by the rector, the staff, or the student. So once you fix a point in this lattice, you can define the low projection of that point and the high projection of the point. Low projection is something which is below. So in particular, in this case, for instance, of the professor and guest. And everything which is not below is the high part. And the high part should not be visible to the low part. That's the key idea of secrecy. We can formulate this theory using a common security definition, which is very popular. And this definition is called non-interference. Non-interference is the formal security definition that we use for programs which work over secret data. So we make this assumption that the attacker is not able to observe termination. And we make the assumption that we are building on top of some arbitrary security lattice. So every variable is labeled with one point of the security lattice. Say, this variable belongs to professor, this other variable belongs to the guest, this other variable belongs to the rector. Starting from this, we build from on top of a notion, which is the notion of L equivalence, where L is an arbitrary label we pick from our security lattice. In particular, we say that two memories, call it mu and mu prime, are L equivalent, which we write as mu approx L mu prime, if and only if, for all the variables which are sitting below the label L, the content of the memory is the same. So from the point of view of an attacker who is sitting at level L, say a professor, the content of these two memories must be identical. In particular, this means that these two memories cannot be distinguished. We might have differences in content which is labeled as rector, but we cannot have difference in content which is labeled as professor. If we build on top of this notion of equivalence, we can formally define non-interference very easily by saying that a program C satisfies non-interference if and only if, for all the labels we pick, so for all the possible attackers, and for all the memories mu1 and mu2 such that these two memories cannot be distinguished by the attacker, if we let the program runs over the two memories and we get final results, then also the final memories that we get cannot be distinguished by the attacker. So intuitively, this means that if we start from two memories which look the same to the attacker, We let the program run on top of the two memories, and we get new memories at the end of the computation. Recall that this is what we get as a result of the big step semantics. Also, the two memories that we get after letting the program C run cannot be distinguished by the attacker. So if the attacker is not able to take any distinction before the computation, the attacker is not able to draw any distinction even after performing the computation. That's the key idea. And we can very easily exemplify that using an example. And for instance, this is the example of the implicit flow that we mentioned. So let's assume for simplicity that we work with a 2-point lattice. So in this lattice, variables are either high or low. In this case, there is a flow of information because I branch over the value of h. I check that this is greater than 5k, and if this is the case, I set the variable L to 0. Otherwise, I set the variable L to 1. We can formally show that this program violates non-interference. To prove that, I can pick two memories, which are low equivalent, so they cannot be distinguished by an attacker which only observes low data. I let the program run, and I get two memories which instead can be distinguished. To show that, let's pick the first memory, mu1, and in this first memory, the variable h is bound to value 6, 7, 8, 9, and the variable L is bound to 0. In the second memory that we pick, variable h instead is bound to the value 1, 1, 1, 1, and variable L is bound to 0. These two memories are low equivalent because they agree over all the low variable, in particular on the variable L. The content of the variable h is different, but attacker is not able to observe the content of the h variable, so this is fine. However, after we execute this program, what we get are two new memories. Sorry, there's a typo here, should be mu1 prime and mu2 prime. We get two memories which instead are not low equivalent anymore. In particular, in the first memory, we will have the variable L, which is bound to 0, and in the second memory, we will have the variable L, which is bound to 1. So this is a violation to non-interference because non-interference requires this property to hold for all the possible memories. Okay, so if we start from two memories which are low equivalent, we must end up in memories which are also low equivalent. And this is not the case for this program. If you think carefully, this formulation of secrecy as non-interference is very, very neat, because essentially, by using a single security definition, we are ruling out both explicit information flows, because if I pick a secret and I store it inside a public variable, I end up being having two memories which are not low equivalent anymore. But at the same time, it also captures the fact that there might be implicit information flows. And we are not happy about implicit information flows because they might exfiltrate secrets, for instance, bit by bit. Is everything clear so far? Do you have questions? Okay, sorry again for the typo. Should be prime here and prime here. Now the interesting bit. We have seen an example of a program which violates non-interference. And showing that a program violates non-interference is useful because it means that the program is not secure. However, proving that non-interference is violated is simple. I just prove that there is a counterexample. However, proving that non-interference holds is much, much, much more complicated. If we check the definition of non-interference, we realize that the problem of non-interference requires us to quantify over all the possible attackers and over all the possible memories. And in particular, we have an unbound set of memories because a memory is a mapping from variables to integers. And so since we have an infinite number of integers, we need to quantify over an infinite set. So there is a universal quantification that we cannot just test. We cannot just try out all the possible memories because we have an infinite number of possible memories. So in general, as every time in math and computer science, once we want to prove that a property is true, we have to prove that this property is true for all the possible examples. So at the moment, if we wanted to prove that a program is indeed secure, so it's a program which satisfies non-interference, with the current set of tools we have is that we should come up with a manual proof, okay? As a simple example, let's assume I have a very simple program which says that I pick the variable L and I store inside this variable L the content of the variable L itself. This program is trivially secure because there is no computation over private variable. But this is a manual argument, right? So I inspected this program and I told you that this program is secure because some condition hold. And this is a pain. If I have a complicated program, think about a real-world Android application, and I want to prove non-interference for that Android application, this is going to be a pain. The good news is that it is possible to automate proofs of non-interference. We can apply these ideas to real-world languages, but for simplicity, we apply this idea just to the simple language which we consider, which is IMP. In particular, we discussed yesterday that in the case of IMP, we had some programs which we didn't like. And the programs we had which we didn't like were programs which were using variables with the wrong type. For instance, we had programs where we stored some integer inside a variable, and then we were branching over the content of that variable, which is ill-typed. The good news is that we can adapt the theory of typing to reason about security of programs as well. So rather than having programs which are well-typed and programs that are ill-typed, we have programs which are secured or not secured based on a typing proof. In particular, as I said, once you want to define a type system, you need to define the shape of the type root. The key insight of our security type system is that our security type system tracks the flow of confidential information inside public variable. And if we notice that there is a flow of public information inside a confidential variable, we reject the program. However, we said that capturing this flow of confidential information inside public variable is not straightforward. In this case, there is no direct flow of confidential information inside private variable, inside public variable, because in this case, I'm assigning to variable L the value 0, and in this other case, I'm assigned to the variable L the value 1. So from a point of view of information flow, this looks fine, but the problem is that this assignment of public information inside other public information happens inside a branch of a conditional which depends on a private data. So there is a leakage of confidential information, not necessarily by this instruction alone, but because this instruction is performed inside a context which depends on confidential information. If you want to develop a type system for a language like this to reject malicious information flow, we have to keep track of where assignments take place. And the key idea is that we do that by using a PC label, which is a label which approximates the security level of the program counter. If I'm branching over a secret data, the program's counter itself might be revealing some confidential information. So by raising the value of the program counter label, once we perform conditional and loops, we're actually able to track useful information about the fact that our program is computing over confidential information. And we can use the program counter label to rule out some programs which would be fine by themselves, but were not fine anymore because we execute these programs inside a context which might reveal private information. The type rules we consider in our system are two shapes. The first shape is the one we use for expressions, and the other one is the one we use for programs. So for expressions, we have a simple typing judgment, which says that a given expression E has label L under a given typing environment gamma. So it means that this expression will evaluate to a value which is either confidential or public, intuitively. So this is the label of the final value that we will produce by evaluating the expression E at runtime. And then we have other typing rules instead, which are for programs, and the shape of this typing rule is different because we read these rules as the command C is well typed under the typing environment gamma and the program counter label PC, which means that the program is not exfiltrating any sensitive information. For simplicity in the type system we consider, we do not make any discrimination between integer and booleans, so we don't care about type errors coming from the wrong use of values. We are only concerned about implicit flows and explicit flows. And this is just for simplicity, so to keep the notation light. It is very easy to extend the type system so that we also include inside the type system checks over the use of integers and booleans, but this is not particularly interesting for this lecture. Let's start by discussing the typing rules for expression. So please try to follow the discussion. If something is not clear to you, please interrupt. We said that typing rule of expression has the shape of gamma assigns to the expression E the label L. We have a bunch of possible rules. I show you just a few representative rules because they essentially show you the full intuition of the type system. Let's skip this one for a moment. Let's start from this one. This one is very, very intuitive. This rule says that if I pick a variable X, the security level of that variable is what I get by looking up the typing environment gamma. You recall that gamma is an assignment from variables to security labels. So this guy here has type security label, which is exactly the shape of the typing judgment for expressions. And this is fine. Let's have a look now at this other rule, which is essentially very similar to this other rule. And this rule says that if E1 has security label L and E2 has security level L, then also their sum, their multiplication, and their subtraction has security level L. If we want to reason about this in terms of our standard two-point lattice, if I sum two public data, I also get a public data. And if I sum two private data, I also get a private data. And this makes a lot of sense, right? What's the problem, however, with this recipe? Can you spot something which we don't like? So if we just pick this rule, in our type system, we can make, for instance, the sum of two public variables, and we can make the sum of two private variables, and this is fine. However, we are not very happy with the expressiveness of the type system. So we will reject some programs which instead we might be able to type check. Can you see any of these examples? Think about the following case. I have a pin, and the pin is confidential, and I want to add the number 10 to the pin. Am I forced to reject this program? Let's think about the alternatives. So let's say I want to have a program which picks my pin, which is secret, and adds the value 10 to the pin. Okay? If I say that the result is public, do I have a security problem or not? Please unmute the microphone and speak up. For any of you who wrote in the chat, please speak up.
Yes.
Okay, why do we have a security problem?
Because the attacker can understand the value of the private
data just by subtracting 10.
Yes.
Right. However, if we add the sum of the pin and of the public value 10, if I made the result of this computation private, would I have a security problem or not?
Sorry, can you repeat?
Yeah, so let's assume I have this discipline. So if I have the pin, which is confidential, and I want to sum to the pin the value 10, which is public, then this is allowed, provided that the result of the computation is private. Are we happy with this rule?
I think yes.
Yes, we are happy. Yes. Because we take the pin, we sum 10 to the pin, and then we make this information secret, so the attacker is not able to recover the value of the pin just by subtracting 10 to some information, right? And this is exactly what is covered by this other rule. So this other rule says that if I consider a value like 10, 12, true, false, I can give to this value any type I like. So by checking this rule, this means that if I want to type check something like pin plus 10, since pin will be high confidentiality, I can assign the high confidentiality value also to the 10 number so that pin plus 10 will become also confidential. Okay, so this type system allows us to manipulate only information which is at the same security level, exactly because I can assign every security level I like to standard values. Okay, and this rule is exactly identical to this other rule. We just missed one example, which is the following. What is the meaning of this rule? The rule says that if I'm able to type check an expression E with type L, then I'm also able to assign to the same expression a label which is more restricted. Put it differently, if I'm able to give the public type to something, then I'm also able to give the confidential types to something. So moving up in the security lattice is fine, because if I move up in the security lattice, I'm becoming more restrictive, okay? If you think carefully, this is exactly the same typing rule you use in programming languages like Java, when you are able to subsume something like list to the object type. Because once you move from the list type to the object type, you're doing something which is safe. And the reason why this is safe is because you can do less stuff over object data rather than over the list data. So by moving up in the type hierarchy, you are actually doing a safe information. You are just losing capability. And this is exactly the same idea. If you have something which is public, you can treat it as confidential, and that will be fine because you are just being more restrictive on what you can actually do over the data. Let's consider now the typing rule for commands, and then we will see an example. The key idea of typing rule for command, as I said, is that a command is well typed if it is not leaking information. So if it is complying with our information flow control policy. The first rule says that the command skip is always well typed, because skip does nothing, so it cannot do any harm. Let's check now the rule for assignment. Assignment, of course, is delicate, because, for instance, something which you want to forbid is that we pick some confidential data and we store it inside a public variable. That will be a type error. That would be a type error. And also something which is dangerous is when we try to write inside a public variable, but we do that inside, for instance, a branch, a conditional branch, which depends on confidential information. So this rule works as follows. If I want to type check an assignment, so storing the content of expression E inside the variable X, what I do is I first type check the expression E, and this should have level L. And then I want that L is less or equal than the label of the variable X. And this is needed to avoid that you store confidential information inside public variable, of course. But I don't just use the label L. I pick the join between the label L and the PC label. Because the key idea of the PC label, as I said, is that we erase this label once we move inside a conditional which depends on confidential data. In other words, assignment to low variables is forbidden inside a conditional which is high confidentiality. In particular, you can see that in the rule for conditionals, because once we type check a conditional, what we do is we first type check the guard, we get the label of the guard, call it L, and then what we do is that we type check the then branch and the else branch with a new PC label, which is equal to the original PC label PC that we have, joined with the security label of the guard. So if the guard is high confidentiality, it means that the PC label will move to high, and this means in particular that any assignment to public variables inside a high conditional is forbidden by the type system. We have a similar rule for while, which essentially mirrors exactly the same intuition. So once we want to type check a while, we first type check the expression E, which is the guard. We find the security label of the guard, and we type check the body of the while by raising the current PC label PC with the join with the same security label of the guard. Then we miss a couple of more rules. One rule says that if I want to type check two commands, which are put once after the other one, we just type check the two commands individually. That's super simple. And this other rule here plays the similar role to this other rule for expression. In the case of expression, it was safe to raise the label of the expression. In the case of type checking a program, it is safe to do that using a program counter which is less restrictive. So if I'm able to type check something with a restricting program counter, say high program counter, then I must be able to type check that using a more liberal program counter, call it low. If something is not totally clear to you, we will see an example. Rather, we will see a bunch of examples, okay? And this example should give you a better understanding of the type rules. Let's assume we make this convention that, as usual, H is private variable and L is a public variable. Let's assume I want to type check a program like this. So this program picks the variable H, puts inside H the content of L plus 4, and then picks the expression L minus 3 and puts that inside the expression inside the variable L. First question, is this program safe or not? Are we leaking any confidential information in this program? Did anyone speak up? Don't look at nothing in this slide but this program. Is this program secure or not?
I think it is secure.
It is secure. I mean, it's not putting any private information anywhere. We are putting some public information inside a secret variable, and this is fine from a security perspective, right? Because we are not doing the opposite. So we're not putting private information inside a public variable. We're putting some public information inside a private variable, as this makes sense from a security perspective, because the security variable is protected more than a public variable. And then in this case, we're assigning some public information to a public variable, which also makes sense from a security perspective. What is nice is that this program not only is secure, but it's a program that our type system actually accepts. To understand why this is accepted by our type system, we take a look at the shape of this program. So the shape of this program is a concatenation. So the only rule which I can apply to a concatenation is this rule here on the upper right. And to type check a concatenation, I need to type check both the components of the programs in isolation. So to type check this program, I need to create a branch where I am actually able to type check this part, and then I create a branch where I'm able to type check this part. Then we have to reason about the individual branches. So let's have a look first at the right branch, which is easier. So on the right branch, we can show that the expression L minus 3 is public. So it's something which is low. Intuitively, why is this low? This is low because L is low. 3 is a value, so I can assign every label which I like to the value, call it low. And low minus low is low, okay? Here we are missing a part of the type derivation, which I ask you to complete as an exercise, but it should not be surprising for you that the expression L minus 3 is something which is indeed public. And this is fine because we are storing some public information inside the variable L, which is indeed public, okay? So this part of the proof tree is completed. Let's have a look now at the other part. In the other part, we need to type check first the right-hand side of the assignment. And this amounts to type checking the content of L plus 4. L plus 4, similarly to L minus 3, is something which is low, because it depends on low information, and which is sum with some other information which is also low. So this will be low. And since low is less or equal than high, we are able to store this information inside the variable H. Notice in the assignment rule that we pick the label of the expression, we join it with the PC, and we have to check whether this is lower than the label of the variable according to the typing environment. In this case, the PC label is low. This is joined with low, so it stays to low. And low is lesser or equal than high. So this is fine. Again, here we're missing part of the type derivation, but building this part is straightforward, and I leave you as an exercise. Is it clear that this program is secure and that we are able to type check it? I assume it's clear. If it's not clear, please speak up. And let's consider another example. Okay, again, don't look at the type derivation. Just look at the program. Is the following program secure or not?
Yes.
It's not secure. Let's assume that H is your PIN number.
Okay.
L is a public variable which has a value 10. You put this information inside a low variable, so this means that this is accessible to the attacker, which means that the attacker is able to leak your PIN just by subtracting 10 from L.
Okay, but I understand that they are the same variable. So if the 12 are the same variable, this will be secure.
It's not really secure because, I mean, the content, let's say that the attacker knows everything which is inside L because this is public.
Okay.
So let's say that the attacker knows that the content of L is 10.
Yeah.
You run this program, you get as a result that the content is 1010. Are you able to reconstruct the PIN? Yes. Because you just need to subtract 10 from the content of L.
Okay, if the attacker knows that previously L was 10.
Yeah, and the attacker knows that because we assume that everything which is public is known to the attacker.
Okay, at each step.
The attacker knows, if we check the definition of non-interference, the attacker knows the state of the memory at the very beginning.
Okay.
And draws conclusion of high variables by checking the content of the memory at the end of the run.
Okay, yes, so it's not secure.
So this program is not secure because the attacker knows that the content of variable L is 10. By running this program, the attacker gets access to the PIN just by subtracting 10 from the value of L. And what is nice is that this program is insecure, and this is actually a program which is rejected by our type system. If we try to type check this program, we are not able because we violate the typing rule. In particular, this is an assignment, and since this is an assignment, we have to type check first the right-hand side. So we are forced to give a type to the expression H plus L. Intuitively, which is the type that we expect for such expression? The type we expect for such expression is high because we are adding confidential data with public data, so the result should better be protected. And indeed, we are able to give the high type to this guy because variable H has indeed the high type, and we are able to give to the L variable the high type because the L variable is low, but L is less or equal than high. And if you recall from the typing rules here, you're actually able to raise the label of each expression you like. So although the variable L is low, we're actually able to type check the variable L as high, just because L is less or equal than H. So the variable H is high. The variable L can also be typed as high. And so in particular, it means that the sum of H and L will also be high. However, after assigning this type to the expression, we are not able to type check this assignment, because to type check this assignment, we have to show that the label of the right-hand side of the assignment is less or equal than the label of the variable where we're putting the content. And since this variable is public, we're not able to show that H is less or equal than the label of L. Is it clear?
Yes.
In particular, observe that if you change this program, so rather than assigning H plus L to the variable L, you assign H plus L to the variable H, this program is secure because the attacker learns nothing, right, about the variable, about the value of H. And this other program, which I wrote here, is a program that you can actually type check. And to type check it, you just build the very same type derivation, with the difference that eventually this check here will succeed, because you will compare H against gamma of H, which is again H. So the very same type derivation could be applied to the type checking of this other command, but for this other command, the type derivation will go through, because this check which fails here would rather work. Clear? Another example, conditionals. So let's consider this example. Again, as usual, don't look at anything in the slide, just look at the program. Is this program secure or not? Is this program leaking confidential information in public variables?
No, because there is only age.
Exactly. So we are never assigning anything to public variable. So this program cannot violate non-interference. And indeed, this is a program we are actually able to type check. To see that, this is a conditional. Once we want to type check a conditional, we have to first type check the guard, and the guard is H less or equal than 30. This guy here, I omit part of the type derivation, you can complete it as an exercise. This guy here is high, and this makes a lot of sense because it depends on high confidentiality data. Then what we have to do is, and this is the interesting part, since the guard is high, these two commands here and here are type checked, but notice that the PC label, which was originally low, is upgraded to high. And this is still fine for this program because skip is trivially type checked. And this assignment is something we can do because in this case, We can give, for instance, the public type to 5, and we know that by making the join between the label of 5 and the PC label, which is high, we get high, and this is fine just because we're assigning inside a high variable. So if you apply the typing rule, this is fine. However, what is interesting is that if we modify this program so that we don't assign to H here, but we assign to L, this program will not type check anymore. And there is a very good reason why it does not type check. And the very good reason why it does not type check is that we are actually revealing some information about H just by inspecting the content of the variable L. If after the execution of the program, the attacker notices that L is set to 5, the attacker knows for sure that H is less or equal than 30. So if you replace this assignment here with a different assignment where you assign to the variable L, you will realize that the program is not secure and type checking will fail, because in this part here of the type derivation, the program counter label is high, and so high join high will give me high, and this is not less or equal than gamma of L, which instead is low. Is it clear, this point? I assume it's clear. So now we have a bunch of simple examples, and my goal would be to reason with you about these examples. Then, as an exercise, I ask you to formally try to build the type derivation for these guys here, but we will first discuss whether these programs are secure, so whether these programs satisfy non-interference, and whether we intuitively expect these programs to type check or not. Then you have to take care at home of all the formal details. So try to type check this program and show that what we discussed together now is indeed correct. So let's start from the very first program. First question, is this program secure? So is this program non-interferent? I start to call some random guy based on the chat. Let me extract one of the lucky guys. Voltini. Do you think this program is secure? Please unmute the microphone and speak. Ah, microphones don't recognize. Okay, let's try another one. Cecchini. Do you think this program is secure?
I'm sorry, but I missed the last part of lesson.
Okay, so you're back in town now. So please, do you think this program is secure or not? The first one.
Okay. Yes, because it not look at high variable content.
So this is a program which for sure is secure because it's not working on confidential data at all. And it is possible, you can try at home, to actually type check this program using the type rule we've just shown. Let's try now second program. So Moruzzi, Do you think this second program is secure? Maruzzi? Okay.
Can you hear me?
Yes.
Okay. So I think yes, because sorry. I think no, because I can derive the value of h by increasing L.
Exactly. So this program is not secure.
Yeah.
Because since the attacker has visibility of public variable before the execution of the program, so let's say the attacker knows that L is 0. Once we execute this program, at the end of this program, L will be 34, which means in particular that this is exactly equivalent to an assignment. So this program violates non-interference. And if you try to tape check this program with the rules we've shown, you will see that you are not able to tape check it. Okay? So this is the exercise done. So a volunteer for the third one. I mean, if you say something wrong, it's not a problem. Just try to reason together with me.
Excuse me, it's possible to repeat the reasoning about the second example?
Yes, the second example is insecure, because in our threat model, which is what is formalized when interference, the attacker knows the state of the memory, of the public part of the memory before the execution, and wants to infer something about the confidential part of the memory by checking the public part after the execution. So let's assume that attacker knows that the variable L initially has value 0. The attacker might be able to get the value of H by letting this program run. I want to show you more formally in terms of non-interference, okay? So let's pick this program. This is the program we have. And I want to show that this violates non-interference. So to show that, I have to find two memories, okay, which are equivalent from the attacker perspective. Okay, so let's say that I have variable H, which is set to 20, and variable L, which is set to 0. Okay, this is a first memory. Now let's consider a second memory. And this second memory, we have that H is equal to 50, and L is again equal to 0. From the point of view of the attacker, these two memories are equivalent, right? Because they agree on the public part, but they don't agree on the confidential part, which the attacker cannot see. What are the memories we get after running this program? So after running this program, H will be which is not terminating, sorry. Let me rectify the example a little bit for simplicity. Okay. So here you will get what? 34. Here you will get 34. Here you get is still 50 and L equal to 0. So you can draw a conclusion, right? You can get also something very similar if you don't have this instruction. You just need to pick two different memories. So let's say you pick this is 20 and this is 10, right? After the execution, you will get this is again 20, this is again 10. But what you get is that this guy will be 14 and this guy will be 24, right? So by starting from two memories which are equivalent to the attacker, so the variable L agrees and it is 0, you get memories where the content of the two variables is different. So the attacker is able to draw conclusion about the value of age. In particular, the attacker knows how far is age from yeah, it's much better to use this one. I should update my example so that we have termination, because if we don't have termination, it's a little bit more complicated. So for simplicity, let's reason about this example, okay? I will update it in the slide. Clear?
Okay, thanks.
This is an example where we start using non-termination. Sorry, I wanted to make them in increasing order of complexity. So to make this correct, I have to put h equal to h plus 1 as well. So what about this case? The third one. The third one is an example where the leak of information is enabled by termination, okay? And we said that termination is something that we cannot observe. So this program is secure, according to our definition of non-interference, and we are actually able to type check this program. So you can prove that the third one is both secure and typeable. I want to have a volunteer for the fourth one. Is the fourth one secure?
I think yes, because in the end we assign 0 to L, so we can't get any information about the age.
Exactly. So this is a program which is secure. So this satisfies non-interference. But you will see that this program is not accepted by our type system. Okay, so you're not able to type check it. Last case, again, is an example of a program which is secure. Okay, because in this case, we are always putting L equal to 0. But again, we are not able to type check it. So if you try to build a type derivation for this, you will fail. So as an exercise at home, try to build type derivation for these examples. And I want to conclude here because I had a couple of more slides that we will study the next week. I want to show you that this type system can be proved correct. In particular, we can show that if we're able to type check the command C, then the command C satisfies non-interference. In other words, the type system is sound. So if we accept a program according to the type system is secure. However, as most type system, the type system is not complete. So we have programs which satisfy non-interference but are rejected by our type system. We have already mentioned an example, which is this example here, where you first put H inside L, but then you overwrite the content of the variable L to the variable 0, which is a program which is secure, but this program does not type check. The intuitive reason why this does not type check is that type checking the composition of two commands requires to type check both commands in isolation, and this command in isolation here alone is a command which violates non-interference. So this program is rejected by our type system. Do you have questions? Any question? No? Okay, so sorry for the couple of typos. I will fix them and then upload the slides and the video when it's ready. Next week, we will go on with the discussion of the theory of non-interference. And then we will have a lab class of information flow control. Thanks for attending.
Thank you. Bye.
Bye.